Welcome everybody. We are at 3.4 and we're looking into the impulse momentum theorem, which is this down here. Force versus change in time is equal to mass change in V. And we're going to do this through the phenomena of a guy named Luke Aikins who decides to jump out of a plane without a parachute. This is the video that we watched in class, and if you haven't seen it, make sure you watch the whole thing. It's pretty cool. So what we need to do first, though, to understand how he survives is understand a little bit about impulse momentum and terminal velocity. So we saw that the impulse momentum theorem is equal to force times change in t. And so I can say that this first part is called the impulse. And that's right here, this force times change in t. And what the impulse does is it changes the momentum. So impulse can slow down or speed up the momentum of an object. Well, I guess we need to know what momentum is. Momentum is a letter P, and that's going to equal to just mass times velocity. Now, most of the time when we're looking at momentum or changes in momentum, the mass doesn't really change, but the velocity does. So most of the time we'll see this as change in momentum is equal to mass times change in velocity. So if impulse is equal to force times change in time, then force times change in time is equal to mass times change in velocity. That means that this is also equal to a change in momentum. And that's what we're going to be using throughout this unit, is this kind of understanding that impulse is equal to force times change in time, which is equal to mass times change in velocity, which is equal to a change in momentum. Now, depending on what you are given or what you're looking for, you'll use this equation in different ways, but this is the gist of what we will be doing in 3.4, 3.5, and your final boss challenge. So let's look at this through Bronco. And what we need to know at first is about the skydiving and terminal velocity. So Bronco skydives and parachutes from a stationary helicopter. Various stages of the fall are shown in the positions A through F. Letting downward be positive direction and using Newton's second law, we see A is equal to F over M. That's just F equals MA rewritten. And we have been writing F as the sum of all forces. Well, the sum of all forces in this case, we can also call F net, are going to be equal to the weight force minus the air resistance force. That's what that big R is, the air resistance force. Find Bronco's acceleration at each position. Answer in the blanks to the right. You need to know that Bronco's mass is 100 kilograms, so his weight is a constant 1,000 newtons. Notice, his weight is not changing. He's not eating hamburgers on the way down. So this is another critical distinction. Weight is measured in newtons, and that's equal to mass times some gravitational field. We've been using 9.8 on Earth. Okay. Air resistance R varies with speed. So air resistance is a velocity-dependent force. If there's zero velocity, there's zero air resistance. As you get more and more velocity, the air resistance is going to increase and increase. So Bronco, as soon as he jumps out of the plane or the helicopter, he has zero velocity in the y direction. So if he has zero velocity in the y direction, V is equal to zero, V initial is equal to zero. That means his air resistance force is equal to 0 newtons, velocity being in meters per second. So then his weight force is 1,000 newtons. And so now I look at, okay, his acceleration is equal to the sum of all forces divided by mass. Acceleration is equal to weight minus air resistance force divided by m. So weight is 1,000. The air resistance force is 0, and that's divided by his mass, which is 100 kg. And so we see 1,000 newtons divided by 1,000 kg gives us 10 meters per second squared. Okay? Well, as he starts speeding up, the air resistance increases and increases, increases, increases. In our example here, it eventually gets to 400 newtons of air resistance force. Well, now my weight force, 1,000 newtons, minus his air resistance, 400 newtons, divided by his mass, which is going to be 100 newtons, Let's see, that's 1,000 minus 400. That's equal to 600 divided by 100. We get 6 meters per second squared. So now his acceleration is slowing down. His velocity is not slowing down. He's still going faster and faster, but his acceleration is slowing down. And he's going to get faster and faster and faster until we reach this next position in C. Now in C here, we see that his weight force is 1,000 and his air resistance force is 1,000 divided by his mass, 100. Uh-oh, that's going to be 0 over 100, which is going to be equal to 0. So his acceleration here is 0. And if he is not accelerating, that means he's going at a constant velocity. And this constant velocity is terminal velocity. So here, the sum of all forces is equal to 0, which means acceleration is equal to 0, which means the forces here are balanced, right? This upward force of the air resistance is balanced with this. And so we have no acceleration, and so velocity is constant. And this is a special kind of velocity called our terminal velocity. Now, he has velocity. His velocity is not 0. He's hurtling super fast towards the Earth, but he is not accelerating more because he's reached his terminal velocity. Okay? So I'm going to let you go through the rest of this. Please ask if you have questions. Another great resource is over here, which helps you go through all of the different definitions. And then, of course, you have the practice questions here at the end. Let's see if we can do a little bit to set you up here. So now when we were talking about Luke Aikins, let's see if I can rotate this guy? Rotate. Yes. Okay, beautiful. Now, so now what we did here was we took a look at Luke Aikins, and based on what we did for Bronco, we're going to make this model for Luke Aikins to show him how he's not going to die. So way back in I think the 20s and 30s, the U.S. Army did a bunch of tests on paratroopers, and they found that somebody dies if they fall out of a plane and they hit the ground with more than 10,000 newtons of force. Okay, so 10,000 newtons of force. If it's greater than that, you're dead. So we need to show Luke that he has less than 10,000 newtons of force when he, spoiler alert, hits the net. Now I want, in each one of these, I need a free body diagram. So what I recommend doing is you're going to draw a dot, as we have always for our free body diagrams. You're going to draw it near the bottom in each one. And then we're going to set a line for his weight force. Now, the FG, which is equal to the weight force, for Luke was, let's see, he weighed 80 kilograms. And well, let's use 10 for gravity on Earth, 10 meters per second squared. So that means his weight force is 800 newtons. And what I'm going to do, because his weight doesn't change the entire way down, I am going to copy that here. And I'm going to copy that, move this one over a little bit, and line them up. Oh, yes. And then I'm going to do the same thing here. Okay, so now we are all lined up. Because his weight force doesn't change. That force going down is going to be the same every time. Now he jumps out of the airplane. What happens? Let's see if I look back at Bronco. When he jumps out of the airplane, the velocity is 0. All that we have is his weight going down, and we can look at his acceleration. So we already calculated his weight. And so his acceleration here, let's see, and I want you guys to go through all these captions. Caption 1, are the sum of all forces equal to 0 or not equal to 0? Well, I have no arrow balancing out this force right here. Therefore, my sum of forces is not equal to 0. The net force is just going to be this force downwards, which is going to be 800. Oh, check that off. Net force is 800 newtons. Check. His acceleration, well, we actually said the acceleration. Acceleration is going to be equal to the sum of all forces divided by mass. That is going to be equal to 800 divided by 80, which gives us 10. So he's accelerating at 10 meters per second squared. Check. His vertical velocity, well, when he jumps out, his vertical velocity is 0 meters per second. And of course, we've already said his mass. His mass is 80 kilograms. Okay? All free body diagrams. All forces start from a dot. Okay, my first one started from a dot. Force vectors are correctly sized. Okay, I started them all small because I know this one over here is going to be huge in the upwards direction. Force is correctly labeled. Okay, my force is correctly labeled with magnitude and units. Yes, yes, yes. Used a ruler properly. Well, in my case, I did a straight line anyways, so I am good to go. Okay, so now, using what you know from Bronco, you're going to show what he does when he reaches terminal velocity, and then we need to use the impulse momentum equation for when he lands in the net. The impulse momentum equation, like we said earlier, was Ft is equal to m change in v. Now here, when he reaches terminal velocity, we recorded this from the video, and we saw that was 67 meters per second. Feel free to use that for his terminal velocity. So his vertical velocity here, 67 meters per second. Let's see, his mass, we said was 80 kilograms. So we've got mass, we've got his change in velocity when he gets to the net, so because we have his vertical velocity. What his vertical velocity when he finishes is going to be 0. That's his super final terminal velocity. Now, when he has the time, we recorded that in class 2 from when he hit stop boiler alert, he lands on a net. The time was equal to 1.4 seconds, depending on which class you're in. Okay, so now we have the time of impact, we have his mass, we have his change in velocity, which was 67 to 0. We can figure out the force of the normal force, really, of the net on Luke. And I think it's going to be something huge like this. I'm going to let you calculate that. I'm going to let you go through all these check marks here, and I'm going to let you ask questions that you have. So thanks for checking this out, and I look forward to your learning.